Hey, so this video is going to be on problem number 5 from page 574, which has to do with motion of a particle again, but it's got a pretty intense function, which is represented by the sign and t plus 2 multiplied here. So couple of things to notice before we go into this right away. This is going to be a very calculator heavy problem. I highly recommend using Wolfram Alpha in order to do a lot of your calculations. You certainly can plug all this stuff into a calculator by hand for some parts, but when it comes to the integration portions, you really want to start using technology for that. So Wolfram Alpha or some kind of TI calculator that can handle it, either one would be fine, but don't attempt this by hand. You can, I just don't recommend it. So here's where I would go with this problem. Part A says to find the acceleration when t is equal to 1.3 seconds. So in order to find acceleration, of course, you have to take the derivative, get the acceleration function first. So using product rule, I would take this as -1 times sine of t squared over 4, and then plus your first function times the derivative of the second, which is just going to be cosine of. Remember that for chain rule, the inside does not change at this point, but then you multiply by the derivative of it, which is just 2t over 4. And if I were to clean this up a little bit more, I might call this negative sine of t squared over 4 minus, actually, let's go ahead and take this 1/2 and pull it in front. And then I might multiply the t through. But that's just a personal, stylistic choice. It's not going to be wrong if you leave it as 1/2 t times t plus 2. Okay, so now that we've gotten this far into our derivative function, we actually want to find what the acceleration is at 1.3 seconds. So plug it in. This part you could do by hand, but I do recommend maybe just finding some technology to help you do that as well. Either way, when you plug that in, you should find that your acceleration is something like -2.37. What would that be? Meters per second squared, essentially. So that's going to be your acceleration. And just notice that it's negative. So ultimately that means, if I were a little particle somewhere in space, and here's my origin, I'm just accelerating in the negative direction. That's all it means, is that I'm accelerating in the negative direction. Doesn't mean I'm moving in that direction, but I'm accelerating in that direction. So maybe that's like in your car, you're going forwards, but you're hitting your brakes. That's accelerating this way, even though you're still moving this way. So just be cautious of how you interpret that value. And then part 2 of A says, determine if the particle is speeding up or slowing down at this exact time. So in order to tell if I'm speeding up, I need to know what my velocity is to begin with. And see if, is my velocity in the same direction as my acceleration? So let's go ahead and find what v of 1.3 is. Again, recommending using technology to find that value. I found that value to be -1.35. And so actually that means my acceleration is negative in the negative direction, but I'm also moving in that direction as well. So I am already going in the negative direction and I'm accelerating that way. I'm speeding up. So actually I'm speeding up, not slowing down. So whenever the acceleration and velocity are in the same direction, whether it's this way or the other direction, as long as they're both oriented in the same direction, then you're speeding up. If they're fighting against each other, then you're slowing down. Part B says, find all the times in the interval 0 to 6 that the particle changes direction. So again, try to connect your brain to this physical idea of motion. If I'm changing direction, I might be going forward some amount, and then changing direction. So when I change direction, actually my velocity stops. I come to zero velocity at some point there. So what I'm really asking, or what I'm being asked, is to find when is your velocity equal to zero. You could use technology to find this, but I actually would encourage you to do it by hand. It's a really good algebra solving skill, and it pulls in some trigonometry as well, so I'd like for your skills to be there. If they're not, so go ahead and try this one by hand. I'm really finding when negative t plus 2 sine of t squared over 4 is equal to 0. So think about this using your zero product property, that you're multiplying two things together and you're getting 0. So whenever you multiply two numbers and you get 0, that's because one of them had to be 0. So either t equals negative 2, but you know what? That one's outside of my domain. My domain is 0 to 6. So ignore that. The only other option is when sine is equal to 0. So I like to use my sine graph to try and understand when that happens. When is sine equal to 0? It happens at 0, and at pi, and at 2 pi. So all of the inputs here would give me 0. So I need to find when is my input, t squared over 4, equal to 0, or pi, or 2 pi. So you set up these little tiny equations for yourself and then you solve. Of course, this one, if I multiply by 4 and take a square root, t just has to be equal to 0. If t squared over 4 is equal to pi, multiply both sides by 4, take a square root, and you actually can simplify to get t equal to 2 root pi, because the 4 can come out of the square root and become 2. T squared over 4 is equal to 2 pi, because again, I'm just trying to figure out when is my input going to give me a 0. Multiply by 4, I get 8 pi, and the square root of 8 pi is just 2 times 2 pi, root 2 pi. Be checking these values as you go. You really want to find all of the values that are in this interval, less than 6, right? So 0 to 6. Because you could, keep going with sine. You could go to 3 pi, and then to 4 pi, etc., etc. So you want to be thinking about the largest value where you should stop. And if I calculate that number right now, 2 times root 2 pi, that guy's actually 5-ish. And so I can kind of safely guess that the next one wouldn't work. I also confirmed this with technology and a graph as well, so I know that this is the last value. Obviously, you should be doing something like that for yourself to ensure that you know this is the last value that would work in the domain. Okay, so those are the values where the particle changes direction. It happens at 0, 2 root pi, and 2 root 2 pi. Okay, so I've just given myself a little more space to finish off this problem, but I kept track of kind of the pertinent information that we found so far, mostly being that our acceleration velocity were negative together at the same time, and then when our particle changed directions. So the next part of this problem asks us to find the displacement of the particle at the end of the time period from 0 to 6 seconds. So I started to kind of draw an idea of how my particle is moving, and here's some interesting stuff to notice. So I don't really know exactly where this particle started. I don't know its position exactly at the moment, but I'm just going to place it at some kind of an origin, which can be a bit arbitrary at this time because displacement really is saying from start to finish, how much did you move? So I'm just going to say my start is at some origin that I'll call 0, although that is a bit arbitrary. So if my particle is here, I do know that it only changes direction when it gets to 2 root pi, which is, I think, about 3 or so. So if I do 2 square root of pi, that number is about 3.5. It's about 3.5 seconds. So my point is that at 0, it's going some direction, and then it only changes direction after 3.5 seconds. So at 1.3 seconds, that's between these two values. And it's telling me that my acceleration and velocity are this way. So I know that it starts going in the negative direction, and then at 3.5 seconds, it changes direction and goes this way. And then at about 5 seconds, this is about 5-ish seconds, it changes direction one more time. And then 6 seconds in, we run out of interval to worry about. Because I don't really care what's happening after 6 seconds. But just kind of showing that, like, okay, we're moving backwards to start, and then forwards, and then backwards, and then stop. So if I want to find displacement, guys, here's where I want you to start using technology. You can do an integral on your calculator or using Wolfram Alpha. But your displacement is just going to be from 0 to 6 of your velocity function. Obviously, please write the velocity function in. You're going to have to enter this little guy into whatever technology you use. But when you hit enter and you get your answer, you should get something along the lines of a displacement negative 6.91. So what that means is that based on where the particle started, it's now almost 7 meters backwards from where it started. So that's what a displacement would mean. Now, distance, on the other hand, would be a little different. Displacement will be different because I want to count every step, every piece of motion as positive. So I use some kind of an absolute value function like this. Now you can enter this into your technology as well, but it might be a little more sophisticated even to notice when your particle is going backwards or forwards and account for that by splitting up your integral. So this first interval from 0 to 2 root pi, your particle is moving backwards in the negative direction, so I know that this integral by itself would be negative. In order to force it to be positive, throw a negative sign in front of it, because negative negative becomes positive. Okay? Now I know that it switches direction and it goes positive for a while. So from 2 root pi up to 2 times 2 root pi, or root 2 pi, like this. It's just a positive motion. And so all of this area is going to be positive already. Now, lastly, from that last turn over to the value 6, the particle is going backwards again. It's going to be negative area. So to make that area positive, I'm going to throw a negative sign on it, because the two negatives will cancel to be positive. So from 2 times 2 pi up to 6 of my velocity function will be all of the area together. Now that's something you can run through your calculator piece by piece and then find values for if you choose to do it that way, which I did. Then this negative sign carries down in front. The area under the curve here was negative 7.58. This next piece of area for that integral is 5.85 or 86. And then I'm going to subtract the last piece of area, which if you just put that into a calculator, you will get negative 5.19 or so. And so it's true that these negatives are getting turned into positives because of that, double negative idea. Plus 5.19. And then finally, if you add all those together, you get 18.633. Okay, and that's the final bit of this problem. It takes some pretty advanced, maybe, understanding of when to use what tools. So when do you break out a calculator and use that versus when you attempt something by hand. The book problems don't say anything about not using a calculator. So I encourage you, unless it says no calculator, go ahead and actually break out a calculator, especially for some of these more challenging problems. That's perfectly acceptable. We need to be able to use our technology and our hand skills just about the same level. And both can be really challenging. So anyway, this problem is a great combination of both.